We're going to look at inference in practice. It's more than just knowing how to crunch the numbers and come up with a conclusion. You need to also understand some of the things about how the data was collected and whether it's practically significant versus statistically significant. So it's more than just going ahead and crunching numbers. So you want to ask yourself, where did the data come from? In statistical inference, you need to have a simple random sample or a probability sample, meaning a stratified random sample or a multi-stage sample. Your confidence intervals and hypothesis tests is subject to bad data. If you have bad data collected, you're going to get bad results. So they only work well and are valid when you have good data. So if you get data from uncontrolled experiments, voluntary experiments, or you have a lot of bias in your data, you're going to have bad results. So you got to always be aware of where is the data coming from. It needs to be a probability sample or a simple random sample or a randomized comparative experiment. If you don't have that, you could get in trouble when other people look at it. So once again, you need to have a simple random sample, a probability sample. Your sampling distribution must be approximately normal. And for what we're looking at right now, you must know the population standard deviation. However, when you don't know that, we will be discussing that in the next two chapters. Now, keep in mind that when you're dealing with a small sample size, you can't use your z-test and z-interval, the hypothesis test and confidence interval, because then you're not going to have a normal distribution. However, the central limits theorem says once you get a large enough sample, then your sampling distribution does become normal and you can use it. But when you have a small one, a small sample size, then your central limit theorem does not affect it enough to cause you to have normal distribution. And your margin of error only covers sampling errors. It does not cover all errors of undercoverage, non-response, and other forms of bias, which are often more serious. Well, how small a p-value do you really need to have? Well, it's somewhat in the context of the problem. If it's maybe convicting somebody for life in prison, then you want a really small p-value because you don't want to falsely put somebody in prison for life when they are truly innocent. So if it's a preliminary study, you're not going to want a real small p-value. So it's all in the context of the problem. Also, it's common practice, at least for what we're doing in this book, to have our alpha, our significance level, to be a 0.05 or 5%. There really is no sharp cutoff between a 4.9 and a 5.1, where one's significant and one's not. So therefore, we typically use different magnitudes, somewhat significant, significant, or very significant. If your p-value was really small, you'd say it's very significant. If it was, say, between a 0.1 or 1% and 5%, I would say it's significant. If it's between 5% and 15%, I would say it's somewhat significant. And then there's also the idea of practically significant. Something might come back when you're doing your test that it's statistically significant, meaning it's not due to chance. However, it may not be all that practically significant. Consider the situation of a drug. It may lower the temperature, and it's found to lower it only 4/10 of a degree, and it's got a small p-value, so it's statistically significant. However, the clinical benefits for the temperature reduction are not found unless it's at least 1 degree or more. So in other words, since this is such a small change in the temperature, it's not practically significant. You also want to take a look at the effect size. And look at the context once again that you're dealing with. Now, it may seem small, but maybe in the context it's a big deal. So consider this one here. A computerized testing reduces the average response time by 2 seconds. Doesn't seem like it'd be a whole lot, but in the context of this problem, when it's done millions of times a year times those 2 seconds, that's a big savings. So you got to look in the context of your problem. It's also a good idea not to just do your test. It's a good idea to give your confidence interval along with your test, because your confidence interval gives you a reasonable idea of what's expected for the change. You also want to be aware of multiple analysis. If you conduct a study 20 times and redo it 20 times and get a significance to show up once, that's 1 out of 20. That's your 5%. So you would not expect all 20 of them to be acceptable. So if you run a test many times and you get one to be significant, doesn't mean that the whole thing is. So consider this. We have a standard deviation of 1.1 grams and a mean of 29 grams, and we have 10 measurements. Let's go ahead and conduct our two confidence intervals for a 96 and a 70. So 96, here's your 96, and your inside of your table is your back of your book. It gives you your z asterisk being a 2.054. Here's your formula for figuring out your confidence level. It's always your mean, which we had said was 29, plus or minus your z asterisk, which we had just figured out to be a 2.054, times your standard deviation, which is the 1.1, over the square root of your sample size of 10. And then we get 29 plus or minus 0.07138. If you add your 29 to that and subtract this from your 29, you get these two numbers. These are kind of the ends of your confidence interval. If you lower your confidence level and redo this, maybe at a 70%, here's your 70%, giving you a z star, z asterisk being a 1.036, plugging it in, you get a much smaller margin of error. So a smaller or a lower confidence level is a smaller margin of error. Higher confidence level is a higher margin of error. Keeping in mind that when you're dealing with your sample size, that the larger your sample size, the less spread out your data is going to be in your sampling distribution, because it's going over your standard deviation over the square root of n. But it's not necessarily linear. It's a curved drop here when you're looking at your standard deviation, because the square root of n is not a linear function. However, the larger and larger your sample size, the narrower and taller your sampling distribution will be. Sometimes you're going to have to go ahead and figure out your sample size that would be appropriate for the problem. Well, your margin of error, you know, is z asterisk times sigma over the square root of n. If you do some algebra and solve this for n, you get n equaling z star, or z asterisk, times sigma over m, your margin of error, all squared, tells you your sample size that you would need to obtain a certain margin of error. Now, sometimes your margin of error, or you can't go, sorry about that, you can't get a sample size to be what you want, because sometimes cost or other things are going to limit you for your sample size. Other times you are able to make it a larger sample size to get a certain margin of error. So let's consider that bacteria problem again, where we had our standard standard distribution being 1.1, and we want to go ahead and get a 90% confidence level, but we want a margin of error of only being a half a gram. So we're going to use our formula, 90%, so you go to 90% on your table C, find your Z star or Z asterisk, which is 1.645, multiply it by your margin of error, or I mean standard deviation, divided by your margin of error, figure all that out, and then you got to still square that, meaning multiplying it by itself, and you get 13.1. Now, 13 measurements would be just shy of giving us the margin of error that we would need. So we would need 14 measurements. Whenever you're dealing with finding your sample size, you always need to round up. You might say this is pretty close to 13, yes, but you always have to round it up to the nearest whole number. Now we also need to talk about the power of the test. The power of your test of hypotheses for a fixed level, significance level, is basically the probability of making a correct decision, basically correctly rejecting the null hypothesis when the alternative hypothesis is true. Or you might say it's correctly rejecting the null hypothesis when we should reject the null hypothesis. So, when you're doing your experiment, you want to make sure you have a large enough sample size to detect the magnitude difference that you think is meaningful. Also, if the test is not significant, then you want to make sure you had enough power to be able to detect that change. Now, in general, for what we're going to be looking at, you want to know that the smaller the significance level, or the higher your power, which is really 1 minus beta, you need a larger sample. Now, the beta that we just talked about here is the probability of a type 2 error. So beta equals the probability of a type 2 error. Your power is 1 minus beta, or the probability of a type 2 error is 1 minus power. Now, you're going to have to know what a type 1 error is, a type 2 error is. The probability of a type 1 error you should know is alpha. The probability of a type 2 error is beta, or 1 minus power. And you'll need to know the idea of power, but you're not going to have to calculate power by hand. So let's go ahead and talk about, sorry about that, type 1 error and type 2 error. A type 1 error is made when we reject the null hypothesis, when the null hypothesis is really true. Well, that's really like a false positive. An example would be a pregnancy test comes back saying you are pregnant when you really are not pregnant. A type 2 error is made when we fail to reject the null hypothesis and the null hypothesis is false. That would be referred to as a false negative. A type 2 error is the probability of that is 1 minus whatever your power was. With a false negative, an example of that would be a pregnancy test comes back saying that you are not pregnant when you really are pregnant. Type 2 errors in the court of law. Now, a type 1 error would say you are convicting an innocent person. A type 2 error is when you set a guilty person free. There's a balancing act between making a type 1 error, alpha, and making a type 2 error, which is beta. Down below shows you the 4 possibilities that can occur whenever you are making a decision. You are hoping to get into one of these 2 boxes where you're making a correct decision. But you could be in this box here where you're making a type 1 error, or you could be in this box down here where you're making a type 2 error. But your goal is to be in the appropriate box.